Hi, and welcome to the next video from Workshop 3 in Mplus. This is Janice Cookin. For this video, we're going to be going through Demonstration 7 and Demonstration 8. Now, I recommend that you have Mplus open and Word open, or at least have the Mplus Workshop 3-regression document printed out while you go through this. That particular document provides step-by-step instructions on what we're doing. I will pull it over once in a while, like here. So here you can see what I'm going to be discussing. And there's a lot of documentation. I'm not going to mention all of it, but that's there for you as you go through and study and learn about these techniques. So in this module, we'll look at a variety of examples focusing on variables, models, syntax, and so we'll be looking at a .inp file like this demo w3_demo7.inp file that you have in the screen right now. We'll look at the output, talk about model fit and interpretation. And in addition to using the statmodel.com and the Mplus Users Guide, as I mentioned, I'm going to use the J.W. Osborne site as well. It's a great textbook if you ever have to do a lot of work in logistic regression, is by J.W. Osborne. Okay, so we're going to be using the NELS data set. So let's take a look at this INP file. Again, I have the title and the data. So there's the NELS_mplus.csv. So that's our data set. Here are the variables we're looking at: grad, Z, SES, ZACH, sex, and low SES. In the Mplus Workshop Week 3 in the notes, I'm just going to refer to those as the notes. I define each of the variables. So grad is an indicator of whether the student dropped out or graduates. So 1 equals graduated, 0 equals did not. So that's a dichotomous variable. ZSES is a z-score referring to annual household income. It's continuous. ZACH is a z-score of the composite, some type of composite achievement test. So that's a score of how the student is doing in school. That's continuous. Sex is gender, and it's categorical, 0 and 1. And low SES is a cutoff. So there's some cutoff that's slightly above 0 for ZSES. And if the family is considered low SES, the answer is 0 for no and 1 for yes. So in Demo 7, we see a couple of things here. And actually, I'm going to change this a little bit to make it simpler to start with. I'm going to take this part out. And we're going to have a real basic analysis where achievement is regressed on SES and sex only. So I'm going to run analysis. Now, typically I would run type equals basic first to check the descriptives to make sure the data is being read into Mplus correctly. Again, I'm going to mention this pretty much every week because it just is so important to get in the habit of doing that. Just notice a couple of other things. I have the C interval, that's going to give me confidence intervals, S values if I needed to run a power analysis, or for any other reason I want to simulate this data, I'll put that here. And standardize will provide me with information on typically I won't see R squared unless I put standardized in there. All right, so now I'm going to run this. I'm going to save and run. Because I made some changes, I got an error. So what's my error? I have a new variable included that was not defined, and that is the ZSES2. All right, so I forgot to change that. So I am going to go back to the used variables, and I'll put my semicolon there and a exclamation point there to comment that out. Okay, now it's worked. All right. So here we go. We see a bunch of the fit parameters or fit information, which doesn't make much sense for a linear regression because linear regression uses ordinary least squares and the model is saturated. And this means all possible coefficients are estimated and the fit indices indicate pretty much of a perfect fit, which is what all of that means. So these statistics are not meaningful. Instead, we'll end up looking at R squared. Okay, so here we have the results. We see that both Z, SES, and sex are significant predictors of achievement. We have the coefficients of those variables, and here's the intercept, and here's the residual variance. So that means that after estimating this, the model is estimated so that the residuals have a mean of 0, and that's their variance. If we want to standardize coefficients, they're there. Pretty much the same, not exactly, because ZSES and ZACH are standardized variables. But of course, sex is not, so that's why that one is different. And then when we go down here, we see the confidence intervals. And there it is. Sorry. R squared is right here. Okay, so there's our R squared. So we see that 25.7% of the variance of achievement is explained by this regression. In the write-up, in the notes, I have some information on the interpretation. So I say that multiple regression results reveal that SES and sex are statistically significant predictors of achievement scores. And I go on to describe how you might want to write that up if you were writing up your results. So now I suggest that you try this on your own by defining a new term, ZSES squared. So let's go back, and I've done some of this already. You want to take the comment exclamation point out, so you include ZSES2 here. You want to define it, so we'll include this where ZSES2 is equal to ZSES times ZSES. And then I also want to include that in my regression. So there we go. All right, so hopefully I've got that all right. Now I'm going to run it. All right, so now we see that ZSES is also a significant predictor. I'm sorry, ZSES2, so the squared. So this is no longer a linear regression. This has a squared term in it. And so that is a significant predictor. And now we can go through and look at the same thing, the standardized values and the R square. So it did describe 4% more, sorry, is that right? 0.257. So that's 0.4% more of the variance. So not a whole lot more, but a little bit. But that's how you can get a square term into your regression model. All right, I'm ready to move on to demo 8, so I'm going to pause for a second and get those files up. All right, here we are. I have opened W3_demo8. In this particular regression, we're going to be working with a categorical, actually a dichotomous dependent variable. So this is going to be a logistic regression. We're using the exact same file, the nels_mplus.csv, same variables as well. And so we are communicating to Mplus that this variable grad, which is the variable that indicates whether some or not someone has graduated, is categorical. And I provide some information here on why we do that and what else it tells us. So when the categorical equals option is used, that communicates that the variable is either binary or ordered categorical. And the default estimator is the WLSMV. But when that happens, we end up getting a probit model, not a logit model. So a probit model uses an inverse standard normal distribution of the probability. We actually want a logit link. So we want our model to be this, that the log of the odds, oops, here, let me say before the coefficients, the log of the odds is equal to beta naught plus beta 1 times the ZSES plus beta 1 times sex plus E, where P is the probability of graduation. And so that makes it the logistic regression. In order to communicate our desire for that, we put estimator equals MLR, which is maximum likelihood with robust standard errors. Our regression model statement is grad on Z, SES, and sex. And I see I actually have to make a change here because in a discussion later, we're going to include ZACH, so I have to comment that out. All right, so I'm going to save it and then run it. All right, let's look at the results. I'm going to talk about the fit information a little bit later. But one of the things that's very useful is if you know the proportion of each of the categories for your dichotomous variable, this is a good check to make sure that Mplus is reading the data properly. All right, so here are our results, or the coefficients and the threshold. After you run the analysis, you can look on page 3, and I actually have typed up the regression equation, the log of p over 1 minus p equals 2.717 plus 1.042 times ZSES plus 0.045 times sex. Now, the threshold is basically the negative of the intercept, and that's important to remember. Now, I'm going to take a look at model fit. Model fit output is of interest in this case because logistic regression is a non-parametric technique. So we're no longer using OLS estimation. And a good fitting model may not necessarily be a valid model. The model must always be anchored in a good theoretical framework. And all of these model fits are used to compare models. If your model is nested, you can also use the log likelihood to do a chi-square difference test. So here we look at the log likelihood, the Akaki information criteria, and the Bayesian information criteria. As we do a comparison of models, we always want to look at those. We want these to look and see if changing the model slightly makes those go up or down. We always want them to be smaller. That indicates model improvement. And then we still do have an R squared down here, but it is a pseudo R squared, and it's similar to what's called the Nagelkerke in SPSS. And this R squared, just like in a linear regression, tells us how much of the variance in grad is explained by the model. So my recommendation now is to pause your this video for a few minutes, take a look at the output, and because it does look different than a linear regression output, and see if you can identify what the various components and aspects refer to. And I'm going to put up demo 9, and we're going to talk about that next. All right, here we are on W3_demo 9, and demo 9 uses all the same data and input file, except in the input file has been changed by adding achievement as a predictor of grad. That's the only change, and what we want to do is run this model and compare the results. So I'm going to run it, and we'll look down here, and first I'm going to actually look at the model fit information. And just a reminder that we always want to look at the AIC and BIC, and this has changed. For demo 8, the AIC was 8745, and now it's 8070. So we do see a reduction in the AIC, which means that this model fits the data better than the previous model. And here we see that, once again, I didn't mention that earlier, but sex was not a significant predictor, but achievement is. And the threshold, which is the intercept, has now changed slightly. And our R squared is quite a bit higher. So that kind of ends the explanation of demo 8 and 9. And we will continue with demo 10 in the next video.